Ik open de zitting van de commissie ter beoordeling van het proefschrift en stellingen van Hoang An-ju Jin. I request the candidate to go to the lectern together with the Parnev, please. The title of the thesis that will be defended today in public is Computational in Memory Based on Memoristive Devices. And the Board for Doctors of Delft University of Technology nominated a small committee to evaluate the thesis and to have a discussion with the candidate here in public today. And the members of that committee are Professor Tahouri, Karlsruhe Institute of Technology, Germany. Thank you very much for coming here today. Dr. Yoshi, G.G. Watson Research Center, IBM USA. Thank you also for joining us. And then Professor Kator, KU Leuven, Belgium, and IMEC, also very important. And then Professor Corporal, TU Eindhoven. Thank you all for joining us from outside TU Delft, because we also have members from TU Delft, Professor Bertels, the co-promoter, Dr. Tahoui, and Professor Han Dioui. As the promoter, my name is Peter Wier. I'm the Pro-Vice Rector of the university. I'd like to start the opposition and invite Professor Tahouri to take the floor, please.
Waarde promovenda, I enjoyed reading your thesis. It was a very nice and comprehensive work on in-memory computing and covers many aspects from the technology to the architecture to the application. So,
Professor Tahouri, maybe you pull your microphone a little bit towards you. Yeah, that's much better. Thank you.
Okay. Meneer de Rector, I would like you to read the second proposition, and I have a question regarding that.
Dear candidate, would you instruct your Parnev to read proposition 2?
Yes.
Standing.
Nga, can you please read the proposition number 2?
Proposition number 2. In-memory computing, enabled by emerging technology, blurs the distinction between architectures and technologies.
Thank you.
So the advancement that we had in computing technologies and Moore's law is somehow enabled partly by the abstraction of the technology from different aspects of the design. So for instance, someone who designed the architecture doesn't need to know all the details about the technology. And that makes the designing current system chips that go over 1 billion of transistors is that it is not required to be designed all billion transistors at once. So there is some abstraction and hiding the information. Now, when you are making this proposition that basically this distinction between architecture and technology is blurred, could you clarify what would be the implications on the design flow that starts from system design and specification all the way to physical design?
How clear the opponent? Thank you for your question. For your question, you're asking about proposition number 2 with telling that as an architect, we have to also have some basic knowledge of some knowledge of technology, and that makes it difficult for architect to make the design of a large design. In my opinion, in the past, when we have conventional architecture with very mature technology, like CMOS technology, we have a lot of basic blocks that really well designed. And at architecture, we can, at architecture level, we can just use those blocks and trying to optimize the use of these blocks together. Now with memristor, the situation is different. We don't have well-designed blocks. And the people who are doing logic design they can produce a very good design, but it's not very practical at architecture level anymore. For example, we have adder that designed by fast Boolean logic or implication logic. It seems to be very fast at logic level. But if we combine it, it's difficult to make a good architecture out of it. So the implication that I mean in this proposition is that at architecture level, we have to also know what's happening at device level. And maybe it's not to really go into the logic design to make the design, just to provide some input, just to tell what is the requirement for the logic designer to make a good design that benefit at architecture level. So that's what I mean with the correlation between architecture and technology.
Could you please clarify a little bit more on the interface between, let's say, the architects and technologists? So what kind of information that pertaining to in-memory computing technology that has to be transferred to architecture designers to be able to make use of this technology? I mean, for instance, they don't need to know all the physics of it, but what kind of information that is necessary to be passed to the architect to be able to design an efficient architecture based on this technology?
Your question is what is the information that the design, the logic design have to transfer to the architect? I think one of the important factors is how the technology, how the device, how the component work. For example, if we look at the endurance problem, for example, endurance is a technology problem. So at architect, we don't really need to know the component endurance. But in computation in memory, the different story. We need to know that memory store is not a very good endurance device. So we have to know that instead of performing a lot of write to it and destroy the device, we should try to find architecture of application that using read favor a lot of read, so that we can utilize this characteristic and reduce the stress for the device about endurance.
Okay. Thank you very much. So, Minier Director, I'm satisfied with the answer to this question. So let me follow up with a more technical question. Regarding, in your thesis, you talk about the areas or applications where in-memory computing is beneficial.
Yes.
I'm going to ask you, what are the application scenarios or the computing domains in which the in-memory computing cannot provide any extra benefit compared to existing architectures?
Thank you for your question. Your question is about which application that the conventional architecture will perform much better than computation in memory. In my thesis, I emphasize a lot of time that computation in memory is application-specific architecture. We cannot use it for any kind of application. So if the application is already performed well on conventional architecture, for example, a lot of applications have very low cache miss, which means that either the memory that used for that application is small enough to fit into the cache, into 3 level or 4 level of caches, or the pattern to access the data is really good and really regular, then we actually don't need to bring it to computation in memory because the architecture itself have also a lot of overhead. So in search application, the application that already have very good performance, like have regular memory access and using very small memory, very small amount of data, then it's much better to put it on existing conventional architecture.
Thank you very much. So my last question is about your social proposition. So proposition 7. So, Minier Director, could you ask?
Proposition 7, please.
Nga, can you please read the proposition number 7?
Proposition number 7, equality between men and women is only achieved when men have the capability of bearing babies.
My question is, this is very depressing in a sense that you are saying that it's basically one way of saying that the equality cannot happen. There are many people who choose not to have kids. So at least this is the way, the hope that I see in your proposition, and I'm going to ask on this. So at least for the people who don't want to or choose not to have kids, do you think at least for them the equality can happen?
Thank you for your question. Let's not talk about the personal choice of people. I think when I write this proposition, I remember the saying from Professor Kuhn-Bechtel in our lab. He said that we don't need to reach to equality, we need to reach to equity. So for men and women, I think we have totally different characteristics and totally different responsibilities. So it's hard to reach to this equality. We just need to find a way to treat women like the way that women deserve to be, and also treating men like the way that men should behave. So we don't need to really treat the two gender with the same, using the same way. That's what I mean with this proposition. For your question, whether the people chose to have children or not, it's not related to the gender equality anymore. It's the personal choice, and trying to treat women or different gender with respect is also a personal choice. So I think we can reach there. It's not depressing, at least in my view. It's just how we're going to reach there.
If I want to project it to a more generic subject of diversity, it reads as if that diversity can only happen if all people are white with blue eyes and of 180 centimeter heights, that the typical, let's say, white stereotype. I think we have to work on what evolution has set us back in terms of the diversity and work proactively to make that happen. Thank you very much. So, Minier Director, I'm very satisfied with the answers I received from my
Thank you very much indeed, Professor Tahouri. Dr. Yoshi, the floor is yours.
Okay, it cannot, okay. Verde Promovendus. I enjoyed your thesis, very nice work. I have a few questions. In-memory computation has been dealt with for many years, actually. And in this work, you try to take it from the architectural level. The question, obviously, is that once you do that, you have made so many assumptions in your thesis, especially because some of these techniques are new, that is NVM, that is non-volatile memories. Yeah. But if those assumptions go astray, say, how would the course of this work would change?
Yeah.
I mean, would the predictions be accurate, or they will lead in different direction?
Zikalia, the opponent. Thank you for your question. Your question is about whether if the assumption that I make in this thesis failed, whether computation in memory still stand. In my opinion, is a yes. I think at architectural point of view, we're trying to solve the memory bottleneck in this thesis, and it's based on memoristic device because the device itself enables this computer architecture. But if we, if the memoristic device itself turn into a different direction or cannot be realized, the architecture part of this thesis still stands because we try to solve the memory bottleneck at the end, and that's the real problem. And the way that we're merging the computation and memory, that's the real solution.
Okay, thank you. On the proposition 4, I have another question that is related to big data. That is, there are many accelerators, these days, many startups which are coming up with these accelerators. Yes, big data is a major issue all across because IoT devices, we are talking about almost 10 to the 15 data bytes, literally, petabytes basically. And if you want to crunch that data into this in-memory application and also store it, not only just calculation, but store it, and you have taken it from peripheral side as well as the memory side, right?
Yep.
So how would that really solve this problem, especially huge data that has, is going to bother us or going to pose problems in near future?
Thank you for your question. I need a little bit of clarification. So your question is about how the computation in memory architecture deal with big data problem in the future.
Correct.
Computation in memory have a very big advantage in dealing with big data because what we know about memory store is that it can have high density. So with the same area, we expect to have more capacity. And that's why in one of my work, I present an architecture where we have an accelerator based on memoristic device. And this accelerator have big capacity. So in comparing with FPGA or GPU, the fundamental difference is that we will have bigger memory to store data. And if this can be realized, then we can perform big data application inside this accelerator without have to move the data from the DRAM, from the main memory, to this accelerator, and then wasting the computation resource that we have inside this accelerator. The only thing that I'm concerned about this architecture is that the operation that we now have in the accelerator itself is quite simple. And how we manage the data, how we map the data to this accelerator to make it, to make the controller cost, the overhead of this accelerator small, that's still an open question. For that, I think in the future for computation in memory, we just need a better design. It's possible, but we need a better design.
Okay. And with all the work that you did, nice work that you did, what does the future bring to this work? Meaning, do you think that this will be sort of accepted universally, or do you propose any plans for students who are coming in and pick up your work and continue with this?
Yes, I believe that the work have a lot of unsolved problem still, because during the scope of this thesis, due to the time limit and also the available tool that we have for memory store, I didn't have the chance to really come up with like a set of application or a set of tool that can be used for exploring different kind of architecture, different kind of logic design. So the next step, I think, will focus on at least three main things. The first thing is at technology level or circuit level. At technology, I expect that the technology will become mature at the end. And the assumption that I make is correct. At the circuit level, I hope that we will have better design. The component, the way that we do computation have to be efficient at that level first. And then at application level, I hope that we find some application that is suitable for the design that we make in the circuit design. And then another thing is that we should develop tool and simulator for this in-memory computation. Like I mentioned, now at architecture level, if we use existing tool and simulator, it's difficult to really see the benefit because technology have to be involved there. And then we need simulator as well to explore not only this sim accelerator, sim architecture, but also maybe other type, maybe making the sim accelerator at the main memory, for example.
Okay, thank you. And one last comment, that is your proposition 8. And you said that silence is golden in the Vietnamese, and in Dutch you have to speak out, just the opposite. But I think my comment to that is silence is golden, I think, universally. If you speak out politically correct words, then I think that should be good. But if you speak out something different, not correct, then that could be a problem. Yeah. Thank you, Director. Thank you very much.
Thank you very much. Nevertheless, I would like to have your comments on that statement.
Yes. Thank you for your comment about the proposition. I think it's reflect the way that we deal with things in the Netherlands. I respect that in my culture also, we believe that if you don't know anything, just stay silent. Just be there and listen. And I grow up like that and believe like that. But when I come here, I see that people solve things differently, and it's work. How does people trying to solve a lot of difficult problems, they trying to speak out. They're trying to really talk to each other, even saying things that really direct and hurt each other in the way. But finally it's solved because we be clear to each other and we know about each other's problems, so it's easier to solve. I wrote this sentence because during my PhD, a lot of time I just keep the problem to myself instead of come to my supervisor and just say, hey, I'm having this problem, can you help me to solve it also? And I think that one of the things that I withdraw from my PhD, maybe I don't have to solve it myself. We have a team to solve it.
Thank you very much. Thank you also, Dr. Yoshi. I'd like to invite Professor Kator to continue your position, please.
Dank u, meneer de directeur. Waarde Prof. Wenda. I would first like to appreciate indeed our very effective cooperation on the first part of the thesis. I think you have produced an excellent survey paper there, and I think this is a very, very useful part of your thesis. So you've done an excellent job. And also the rest of the thesis I read with a lot of interest, and would like to ask my questions about that especially. Yeah? In particular, section or chapter 4.2, you go into the interconnection network. Yeah. And maybe it would be good indeed if you project the figure. These are very small letters. I think you have a number of proposals. I think figure 5 is the CMOS based.
And page 140.
Yeah. So page 140. Yeah. So figure 5 is the CMOS based. Figure 6 is the memristor based, and then figure 7 is the hybrid. And it's those that I would like to ask questions on.
140.
Yes.
140.
40.
Thank you.
There we are. Thank you.
you.
Okay, so, and as you mentioned yourself, there are indeed some trade-offs, and there are different ways to use that. Now, I have in particular a question about, if you look at the main metrics, these are delay and area and energy or power.
Yep.
And if you would like to separate them, yeah, so normally there are trade-offs and you want to try to combine. Suppose now I first go only delay, then I go to only area, and then I go to only energy. How would you rate these different proposals, these 5, 6, and 7 figures?
How clear the opponent? Thank you for your question. So your question is to design this method, how can we separate?
Well, especially if I would have delay as the only metric, which of these three would be, according to you, the most suitable?
Okay.
If I have area as the only metric, which of these three would be the most suitable?
Yeah. Your question is whether if we chose only delay, then which one will be the fastest? In this work, I think if consider only delay, we can choose the memristor base. If we chose only delay, we should choose the hybrid interconnect network. And if you